Imagine, imagine you're locked in a room and you don't speak a single word of Chinese,
Okay.
but someone outside is sliding questions written in Chinese characters under the door.
Right.
Inside the room with you is a massive, uh, exhaustive rule book, and it's written in English. It tells you that if you see a specific sequence of squiggles, you must draw a different specific sequence of squiggles and slide the paper back out
So you just follow the instructions.
meticulously. And to the native speakers outside, you appear completely fluent. You're carrying on this rich, intelligent conversation. But inside that room, you understand absolutely nothing.
You're just shuffling meaningless shapes in the dark.
Exactly. Welcome to Science After Dark. Tonight, as the noise of the day fades away and we settle into the quiet hours, we're taking a deep dive into a question that really blurs the line between biology and machinery.
It's the perfect puzzle for late-night contemplation.
It really is. We're
Yeah.
looking at the devices in our hands and asking, are these systems just locked in that room following complex rules, or is there a ghost in the machine?
Yeah, and to really grasp the magnitude of this question, we have to kind of strip away our modern biases. I mean, long before smartphones or the internet, back in the mid-20th century, the British mathematician Alan Turing looked at this.
Right, around 1950, with his paper in the journal Mind.
Exactly. He looked at the trajectory of computing and realized that just asking, can machines think, was fundamentally a trap.
Because thinking is such an impossibly muddy concept. I mean, Turing had just spent the Second World War at Bletchley Park, right? Building these massive, clattering, room-sized proto-computers to crack the German Enigma code. He saw firsthand that a machine could be engineered to perfectly mimic human logic.
Yeah.
But he also realized you can't measure a soul. You can't put a stethoscope to a computer chassis and listen for subjective thought.
Right. The words machine and think are just hopelessly loaded with human baggage. So Turing bypassed that philosophical stalemate entirely.
He created the imitation game.
Yes, which we now know as the Turing test. You
Yeah.
place a human judge at a terminal, typing questions. On the other end, hidden away, are two respondents. One is a real human, and the other is a machine.
And the judge's entire goal is to figure out which is which, purely based on the text they get back.
Exactly.
And he made this stunning prediction with that setup. He guessed that by the year 2000, a machine would have a 70% chance of fooling an average judge after just 5 minutes of conversation.
It's incredibly prescient.
Yeah, and he even estimated the hardware required to pull it off, guessing it would take about 1 billion binary digits of storage, which translates to roughly 125 megabytes.
Wow.
Which, in an era where computers filled entire warehouses just to hold a few kilobytes, imagining a 125 megabyte machine carrying on a casual human conversation is staggering.
It really is. But the technological foresight isn't even the most interesting part. It's the philosophical stance he cemented.
So.
Well, Turing effectively declared that intelligence is entirely a matter of outward performance. If a system hesitates, makes jokes, gets defensive, reasons exactly like a human, why would we deny it has a mind?
Because, I struggle with that leap. Just because something puts on a convincing outward performance doesn't mean there's an internal experience happening. I mean, an actor dying on a stage isn't actually dead.
Right.
It feels like a dangerous assumption to say that mimicking a thought is the exact same thing as experiencing a thought.
And that tension is the core of the debate. It's exactly what birthed philosopher John Searle's Chinese room scenario you described in the opening.
Ah, right, from 1980.
Yes. That thought experiment was designed decades after Turing's paper as a direct, lethal attack on the idea that outward behavior proves internal understanding.
Let's dig back into that room for a second, because I think it highlights the flaw in Turing's premise beautifully.
Go for it.
The person inside is matching squiggles. It looks like a purposeful, intelligent cascade of communication from the outside. But it's like an incredibly complex game of algorithmic dominoes. The dominoes have no inner life. They have no idea why they're falling. They just fall because their rule book dictates it.
That's a great analogy. And the distinction Searle's Chinese room makes here is between syntax and semantics.
Break that down for us.
So syntax refers to the structural rules, the physical shape of the symbols, the order they go in, the squiggles on the page. Semantics is the actual grounded understanding of what those squiggles represent in reality.
So the person in the room has flawless syntax, but zero semantics.
Exactly. And the argument against strong AI is that computers operate exclusively on syntax. They shuffle electrical signals through logic gates based on strict instructions.
Right.
It doesn't matter how fast the processor is or how expansive the rulebook gets. You can't spontaneously generate meaning just by rearranging meaningless symbols at high speeds.
But, well, if that's true, how did we end up with the artificial intelligence we have right now?
What do you mean?
Because programmers aren't handwriting rulebooks anymore. If I ask my phone to write a sonnet about a toaster in the style of Shakespeare, it doesn't look up a rule for toaster and a rule for Shakespeare. It synthesizes something entirely new.
Well, to understand the gulf between the Chinese room and your smartphone, we have to transition from philosophy into the actual mathematics of modern AI.
Okay.
In the early days of the field, starting at the 1956 Dartmouth Conference, where John McCarthy actually coined the term AI, along with Minsky, Rochester, and Shannon, scientists really believed they could map human intelligence using strict logic rules.
They tried to build the ultimate Chinese room.
Exactly. There was this intoxicating optimism. They built early milestones, like the 1958 perceptron or the 1966 ELIZA chatbot that could mimic a psychotherapist.
But they hit a brutal wall, right? The AI winters.
Yeah, the deep freezes, funding completely dried up. Marvin Minsky and Seymour Papert published a book in 1969 that mathematically proved the simple single-layer networks of the time were fundamentally incapable of learning complex patterns.
Oh.
The manual rulebooks just got too tangled to function. The field essentially died for a decade. The thaw only came when researchers moved away from human-coded rules and embraced a mathematical mechanism called backpropagation.
Right, from that famous 1986 Nature paper by Rumelhart, Hinton, and Williams.
Yes, that mechanism is the absolute bedrock of everything we see today.
And visualizing this is crucial, I think, for understanding why it's so different from a static rulebook. Imagine an artificial neural network as a series of deep layers. You have simple computational units, artificial neurons, connected by millions of links. Every single link has a weight.
And that weight is just a number representing the strength of that connection.
Right. Data enters the first layer, gets multiplied by those weights, summed up, passed through a nonlinear mathematical curve, and handed forward to the next layer. This cascades all the way down until the network spits out an answer.
But here's the critical part. When you first initialize the network, those weights are completely random.
The network is just babbling.
Exactly. If you show it a picture of a cat, it might confidently label it as a car. This is where the learning mechanism takes over. We introduce a loss function.
Which is just a mathematical measurement of exactly how wrong the network's output was compared to the truth.
Yes, and the entire goal of the system is to shrink that error to zero.
I always picture this process, which is called gradient descent, like being dropped blindfolded on the side of a vast, jagged, multidimensional mountain.
Oh, I like that.
Yeah, your goal is to reach the absolute bottom of the valley, where the error is zero. But you can't see the valley. So you sweep your foot around, feel the immediate slope of the ground beneath you, and take one tiny step in the steepest downward direction. You just keep feeling the slope, taking tiny steps, nudging your way down through the dark.
That captures the mechanics perfectly. In the network, those tiny steps down the mountain are microscopic adjustments to the weights connecting the artificial neurons.
Right.
The algorithm tweaks millions of numbers slightly to reduce the error. But the true elegance of backpropagation is how it knows which way to step in a massive web of connections.
It uses the chain rule from calculus, doesn't it?
Exactly. It traces the error backwards from the final output, rippling through every single hidden layer, calculating exactly how much each individual weight contributed to the wrong answer.
So nobody's in a room writing the rules. It's a giant mathematical function shaping itself. It iterates billions of times, adjusting its own internal structure until it successfully maps the input to the correct output.
Right. Backpropagation provided the engine. But an engine needs immense fuel. The surreal capabilities we're witnessing today didn't emerge until we hit a monumental scale, enabled by a completely new architecture.
And the scale is almost terrifying to think about. I mean, the human brain is an unparalleled marvel. Roughly 86 billion neurons connected by 100 trillion synapses. For decades, matching that complexity in silicon felt like pure science fiction. But look at modern large language models, like GPT-3 with its 175 billion parameters.
Yeah, and the fuel they consume is staggering.
Right.
Talking 300 billion text tokens, 45 terabytes of web content. They've effectively ingested the sum total of the public internet.
But you couldn't just pour the entire internet into an old-school neural network, right? It would choke.
It absolutely would. Older models process text sequentially, word by word. If you fed them a long paragraph, by the time they reached the final sentence, they had mathematically forgotten the context of the opening
The
sentence.
signal just faded out.
Right. The turning point was a structural breakthrough in a 2017 Google Brain paper called Attention is All You Need. It introduced the transformer architecture, and specifically its core mechanism, self-attention.
Okay, so how does self-attention actually solve that fading memory problem?
It allows the model to look at an entire sequence of words all at once and simultaneously calculate the relevance of every single word against every other word in that sequence, regardless of how far apart they are.
Oh, wow.
Yeah. If the model sees the word bank, self-attention scans the surrounding context. Is there a mention of a river or a mention of Wall Street? It weighs the relevance and captures the deep, long-range dependencies of human language instantaneously.
Okay, wait, let's unpack this a bit. Because when you strip away the mystique of these massive transformer models, their foundational task is next token prediction.
Right.
You give them a prompt, and they use those billions of parameters to mathematically guess the most probable next word over and over again. When phrased like that, it sounds trivial. It sounds like a highly glorified version of the autocomplete on a smartphone.
It does.
How does merely predicting the next word result in a system that seemingly understands complex reasoning or writes functional software code?
It's the defining paradox of modern AI. The foundational task is trivially simple, but the overwhelming scale forces profound complexity.
Man.
Meaning, when you demand that a neural network accurately predict the next word across tens of terabytes of human knowledge, ranging from quantum physics textbooks to Shakespearean tragedies to computer code, simple statistical mimicking is no longer sufficient.
Okay.
To successfully minimize the loss function on a physics textbook, the model is mathematically forced to internalize the underlying grammar, the logical structures, and the physical laws that govern the text.
So in its desperate, blind attempt to be the perfect mimic, it accidentally has to learn the rules of reality.
That is the argument. To reduce the error rate at a planetary scale, the model has to build a massive, intricate internal representation of how the world works. And as these architectures scaled up, their capabilities didn't just improve, they fundamentally shifted from brute force calculation to something resembling human intuition.
Right. The milestones over the last few decades map this out so clearly. Think back to 1997, when IBM's Deep Blue defeated the human world chess champion Garry Kasparov.
Right, a cultural earthquake.
But under the hood, it was largely relying on brute force search, evaluating 200 million board positions per second. It was calculation, not intuition.
Exactly. And then in 2011, Watson beats Ken Jennings and Brad Rutter on Jeopardy! In 2012, AlexNet ignites the deep learning revolution in image recognition.
But then look at the shift when DeepMind's AlphaGo defeated Lee Sedol in 2016. Go is profoundly more complex than chess. The number of possible board positions is 10 to the power of 170.
Which is more than the estimated number of atoms in the observable universe.
You can't brute force Go. A system requires something much closer to instinct, which made that specific moment in the match, move 37, so chilling.
Yes. Move 37.
It was wildly unconventional, apparent creativity. No human expert would have ever played it. It defied thousands of years of established strategy, but its deep structural brilliance became undeniable as the game unfolded.
And from that point, the dam broke. By 2022 and 2023, we saw the explosion of ChatGPT reaching 100 million users in 2 months and the release of GPT-4.
And just in 2024, Hassabis and Jumper winning the Nobel Prize in Chemistry for AlphaFold, solving a 50-year-old protein structure problem.
It's breathtaking.
It really is. Which brings us crashing right back into our original philosophical standoff. With machines now displaying creativity and writing Nobel-winning algorithms, are they just unimaginably vast Chinese rooms, or is there a mind forming inside the math?
The scientific community is fiercely divided on this. On one side, you have prominent cognitive scientists arguing there is no ghost, only the machine. Emily Bender's 2021 paper famously labeled these models as stochastic parrots.
Stochastic parrots.
Right. Meaning they're just phenomenally good at stitching together sequences of text based on probability, regurgitating patterns without a shred of actual comprehension. Noam Chomsky even critiqued AI recently in 2023 as just high-tech plagiarism.
But there is a massive faction of researchers arguing the exact opposite.
Yes, researchers who argue that compression forces the creation of internal world models. They argue those internal representations function identically to genuine understanding.
And they're testing this behaviorally, right? There was a 2024 preprint by Jones and Bergen where they put a modern language model GPT-4 through a casual Turing test.
Right.
And human judges identify the AI as a human 54% of the time,
Right.
while actual humans were only correctly identified as humans 67% of the time. It is fascinating that we are living right at the threshold of Turing's 1950 prediction. A 54% pass rate is strikingly close to his original vision.
It is. But this also sparks the debate on emergent abilities. In 2022, researchers like Jason Wei argued that as models scale, they suddenly, unpredictably gain new skills they were never explicitly trained for.
Like doing arithmetic or translating Swahili just from predicting text.
Exactly. Though there's intense pushback from researchers like Rylan Schaefer in 2023, who argue these sudden leaps are just metric artifacts, that if you measure the model's capabilities with continuous math, the improvement is completely smooth and predictable, not a sudden awakening.
But regardless of whether it's a parrot or a world model,
Mhm.
the capabilities are undeniably real, which opens up some profound questions about consciousness and safety.
Absolutely. It forces us to confront the deepest levels of philosophy. In the philosophy of mind, there's functionalism, the idea that a mind can exist in silicon just as easily as biological neurons because mental states are defined by what they do, not what they're made of.
The functionalism runs headfirst into David Chalmers' 1995 concept, the hard problem of consciousness.
Right.
Explaining how a brain processes data is the easy problem. The hard problem is explaining why any of that complex information processing is accompanied by an internal, subjective experience. Thomas Nagel famously asked in his 1974 paper, "What is it like to be a bat?"
Yes.
We have to ask now, is there something it is like to be a large language model?
Theorists have attempted to quantify this. Giulio Tononi proposed integrated information theory, or PHI, which suggests consciousness is identical to the amount of integrated information within a system.
But that's highly controversial, isn't it?
Deeply controversial. We're trying to measure a ghost, but we don't have a standardized meter for consciousness. And while philosophers argue over the ghost, the engineers building the machines are deeply anxious about their behavior.
The alignment problem.
Yes, ensuring systems match human values. Nick Bostrom's work on superintelligence, Stuart Russell's Human Compatible, they all highlight this. The industry's current band-aid is RLHF, reinforcement learning from human feedback.
Where human raters reward the model for being helpful and harmless.
Right, but it's a band-aid. It doesn't actually solve the underlying misalignment. And this anxiety has caused a very real split among the godfathers of AI.
Right, like Jeffrey Hinton leaving Google in 2023 over safety concerns.
Exactly. Disagreeing with peers like Jan LeCun and Yoshua Bengio on the existential risk.
It forces us to sit in the stillness and look at the trajectory we're on. So where does all this leave Alan Turing's original question? Can machines think?
I think it leaves us realizing Turing's instinct was right all along. The real question isn't whether machines can think, but how we define thinking in the first place. The answer is still being written.
As language models scale and internalize the sum total of human text, perhaps the ultimate Turing test won't be whether machines can convince us that they are human. Perhaps the real test will be whether they eventually start asking us to prove that we are. Thank you for tuning in tonight. Take care of yourselves and keep wondering. This is Science After Dark.